Hi everyone, this is Jake Fry, and today I'm going to continue our discussion in 1D kinematics with a special case known as freefall. And another way to think about freefall is in a case that just has constant acceleration. Okay, so what is freefall? In essence, it's a special case where an object is only experiencing one source of constant acceleration. Typically, this acceleration is due to gravity, hence the part of the name fall. And the value commonly used for the acceleration due to gravity is 9.81 meters per second squared. This is an average value taken across all of the Earth, but it does change by a little bit based on the density of the ground of the Earth below you. But just by using 9.81 meters per second squared usually will be good. You could also round that up to 10 meters per second squared for a lot of the problems that you'll be doing. Alright, but that gave us fall. What about free fall? In order to be free fall, no other forces can affect the acceleration downward, such as the force due to air resistance. And I know I'm saying a lot of things with forces, and I haven't yet described what forces are and what they mean, but all we need to know for now is that forces are a type of vector that cause a particular object to have acceleration. Alright, so now where does this idea of free fall come from? So, in Western history, we like to think that it comes from Galileo Galilei, which isn't exactly true, but it works well for us to, ground us in Western culture, I guess. And so, anyway, in the 16th century, Galileo Galilei was a mathematician working in Pisa, and he developed the basic properties of free fall. And so there's a commonly known experiment that he most likely only did as a thought experiment, where he looked at the famous Leaning Tower of Pisa and tried to imagine what would happen if he dropped two objects of different masses and different sizes from the top of the tower. Which one would reach the ground first, and which one would be moving faster when it reached the ground? So, the old idea was from a Greek, mathematician, Aristotle, and it was a theory that more massive objects, so either heavier objects, so massive, or objects with larger volume, would fall at a faster rate than smaller or less massive objects. And Galileo and other mathematicians outside of the Western world that are lesser known, slightly before him, determined that this is actually not the case and that they would fall at the same rate. So what are the properties that he, theorized and then later discovered? So, the first one is that objects dropped at the same height will hit the ground at the same time and with the same speed. And the second is that all objects, regardless of their mass, have the same rate of acceleration when they fall. Cool. And so, can we use these ideas of constant acceleration of something falling to extend it to other similar systems that are completely linked based on mathematics? So, the answer is yes. So, for example, if we have a truck and a bicycle, so two objects that are very different in terms of mass and size, both accelerating towards an intersection from rest. So they start with zero velocity, and they are accelerating towards an intersection, and they start at the same location as well. And they accelerate at a constant acceleration. So what will happen? So both will reach the intersection at the same time and same speed, since mathematically there's no difference to the falling object scenario. So all you need to do in your head is rotate your coordinate system by 90 degrees. So instead of the constant acceleration pointing down, like in a falling case, now it's pointing horizontally, because both the truck and the bicycle are accelerating at a constant rate towards a common intersection. Alright, so now we've only talked about objects starting from rest. So does adding some initial velocity change anything to the problem? So say you have two objects that are very different in size and mass, a bowling ball and a ping pong ball. and you throw them upward with an initial velocity where the velocities are the same for the two balls. And will they fall back down and hit the ground at the same time and the same velocity as each other? So turns out yes. So the way that I like to think about this is that when you first throw them up, the velocity will start to decrease due to the constant acceleration that's common to both until they reach a zenith in height at the same time, and their zenith in height, they would have zero velocity. So then they would start to drop. And so once they reach that initial zenith in height, the problem will be identical to the one where we dropped them from rest at a certain height. So all that changes is that, where we start our time clock is shifted backwards in time so that they have time to reach the maximum height before they fall. Okay, so hopefully that makes sense. So what about if we were to throw the balls downward with an initial velocity? Would they hit the ground at the same time and the same velocity as each of the two balls? So in this case, again, yes. So while we don't have exactly the same scenario, so we can't change our time axis in order to say, try to make it exactly identical to dropping the two objects, since we've pushed them downwards and the acceleration will always make it speed up the velocity downwards towards the ground. It's just an offset in the overall velocity when you shove them downwards. So they'll both hit the ground at the same time and with the same speed as the other object. And so this is kind of like, just having a good picture in your head, but we can always go back to our original kinematic equations in 1D. And so we see that for each of these, we have things like an initial velocity, v naught. And so definitely not changing the initial velocity won't have any difference in terms of the velocity when you hit the ground. And so yeah, hopefully all this makes perfect sense.